3% of the people on this planet have a form of hearing loss that no hearing aid and no cochlear implant has ever been able to fix, and a lab in China just proved, in a deaf rabbit, that it doesn't have to stay that way. That is not 3% of some rare, obscure condition. That is roughly 1 in every 30 people you will ever meet, enough that in an average classroom, an average office floor, or an average family gathering, someone in the room is affected. And for every one of them, the reason nothing works isn't really the ear at all. It's the wire behind it, the auditory nerve, and once that wire is cut or missing, even the most advanced, most expensive cochlear implant on Earth has nothing left to plug into. The team that just cracked this problem sits at Nankai University in Tianjin, led by a professor named Xu Wentao, and what they built is not a better hearing aid and not a better cochlear implant either. It is an entirely new nerve. Stick with me, because the way this thing actually works is stranger and more elegant than anything currently sitting in anyone's ear canal. And by the end, you'll understand exactly why doctors are calling this a genuinely different category of device, not just another incremental upgrade to something that already existed. For nearly 50 years, the entire hearing restoration industry has run on one basic idea. If the ear itself is broken, skip it and talk directly to the nerve. That is what a cochlear implant does. Since the first single-channel devices of the 1970s, it threads a string of electrodes into the inner ear and fires tiny electrical pulses onto the auditory nerve. And for the overwhelming majority of deaf and hard-of-hearing patients, it genuinely works. Companies built a multi-billion-dollar global industry out of that one trick, refining the electrode count, the software, and the surgery itself generation after generation for half a century, and for patients with an intact nerve, those refinements genuinely changed lives. Xu Wentao wasn't originally trying to fix hearing at all. Back in 2018, his lab published the world's first flexible artificial tactile nerve in the journal Science, essentially teaching a piece of electronics to feel touch the way real skin does. That project turned into an 8-year mission, now run by a team of more than 40 researchers with an average age under 30. Build an entire family of artificial senses, one at a time, each engineered from scratch, with his own group holding the underlying patents on all of it. Touch came first, back in that original 2018 paper, and sight, smell, and taste followed over the years after that. By the time his group finally turned to hearing, they weren't newcomers chasing a trend. They were finishing the last chapter of a decade-long blueprint for replacing human senses with electronics that behave like the real thing. But here is the part cochlear implants have never solved, no matter how many electrodes engineers cram into them, and no matter how many decades of refinement go into the software. Every cochlear implant ever sold shares the exact same blind spot. It can pick up sound perfectly. It can convert that sound into an electrical pulse perfectly. And then it hits a wall, because it still needs the patient's own auditory nerve to carry that pulse the rest of the way into the brain. Think of it like a phone company that has fixed every mile of cable running toward your house, replaced every switchboard, upgraded every satellite along the way, except the last few feet between the wall socket and the phone itself. If those last few feet are cut, it does not matter how flawless the rest of the network is. The call never completes, no matter how good the signal was a moment earlier. For patients whose auditory nerve is severely damaged or simply absent altogether, that is exactly the situation they're stuck in. Doctors consider it one of the last true walls left in hearing restoration, because unlike almost every other limitation in this field, you cannot solve it with more electrodes, better software, or a more skilled surgeon. You cannot stimulate a nerve that isn't there, no matter how advanced the implant sitting next to it is. So the real question stopped being, how do we build a better cochlear implant, and became something far stranger, something that sounded almost like science fiction inside a hearing research lab. Could you build an artificial replacement for the nerve itself? One that skips the broken wire completely and routes around it entirely? That question is exactly what Xu's team answered, and they didn't answer it in theory, sitting somewhere in a simulation or a patent filing. In live trials, rabbits that had completely lost their auditory nerve regained the ability to recognize spoken commands and act on them correctly, completing matching tasks that required genuinely understanding what they'd heard, not just flinching at noise. And they did it through a device that never once touches the original damaged wiring, because it doesn't need to. It builds its own path instead, from microphone to brain, with nothing in between. If a video like this is useful to you, subscribing helps more of them reach you, and it costs nothing. Now, here's how they actually pulled it off, piece by piece. Here is the shape of what they actually built. Instead of a wire hooked up to a fixed number of electrodes, the device is a compact system with 4 jobs stacked into one continuous loop. It listens, it encodes, it decides what matters, and then it fires that decision straight into the nervous system, bypassing the damaged nerve completely. The first piece is the microphone, and it does not need a battery to run. It is self-powered, generating its own tiny electrical signal directly from the vibration of sound itself, roughly the same way rubbing 2 balloons together generates a spark of static electricity out of nothing but friction. That signal becomes the raw material for everything that happens downstream. And because it needs no external power source, no battery to replace, and no charging case to carry around, it can sit inside the body indefinitely without ever needing to be opened back up. The second piece is where the real trick lives, and it is the one idea worth holding on to for the rest of this video. A chip shaped like a 6-pointed star, built specifically to do one job hearing devices have never done well. Focus. Picture a crowded restaurant. Somewhere in that noise, one voice is talking to you, and your brain, effortlessly, tunes out the clattering plates, the scraping chairs, and every other conversation in the room to lock onto that one voice. That isn't really your ears doing the work. That is your nervous system actively suppressing everything except the one signal it has decided matters, in real time, moment to moment. Engineers call the underlying trick lateral inhibition. Strengthen the pathway you want, and simultaneously choke off the pathways competing with it in real time, dozens of times a second. The star-shaped chip inside this device is wired to do exactly that job artificially, letting one voice through a noisy room instead of drowning the patient in one undifferentiated wall of sound, which happens to be the single biggest complaint about hearing aids and cochlear implants alike, and the main reason so many users quietly give up on them the moment they step into a restaurant, a classroom, or a crowded street. Solve that one problem, and you solve the complaint that sends more devices back into a drawer than any other. The third piece handles memory and timing, and it is built from something you would not expect to find inside a medical implant, a material called tungsten trioxide, arranged into nanowires. Picture thousands of microscopic tide pools, each one able to hold a little more or a little less, slowly draining and refilling over time depending on conditions around it. Inside this device, instead of water, tiny charged particles move in and out of these nanowires, and that gradual reversible flow lets the chip hold onto information the way a biological synapse does, fading in and out smoothly rather than snapping on and off like a light switch. That is the core weakness baked into every conventional cochlear implant. It fires on a fixed clock, in rigid on-off pulses, which is exactly why speech in a noisy room turns to mush no matter how loud you turn it up, and why so many implant users describe voices as sounding robotic or flattened. This tide pool-style memory gives the new device something closer to a continuous, analog feel, instead of a stutter of digital pulses arriving on a rigid schedule, which is a large part of why researchers believe it could eventually handle speech and noise far better than anything on the market today. The fourth piece solves a problem hearing devices. Barely even attempt, knowing where a sound is coming from in 3-dimensional space. The team built a grid of 64 microscopic synaptic transistors, arranged 8 by 8, essentially 64 tiny listening posts working in unison. By comparing the small differences in signal across that entire grid, mathematically, transistor against transistor, the system can calculate not just that a sound happened, but roughly where it happened in 3 dimensions, the same way your brain currently uses the tiny timing gap between your 2 ears to tell you a car is approaching from your left before you ever turn your head to check. No single hearing aid on the market today attempts this kind of spatial mapping at all. Put all 4 pieces together, and you get a closed loop that behaves less like a microphone bolted onto a nerve, and more like a nerve itself, sensing, focusing, remembering, locating, all before the signal ever reaches the brain, and all without ever needing the original damaged nerve to carry a single pulse. That is the actual leap here, and it's easy to miss underneath all the individual components. Earlier hearing technology tried to make a broken system work a little better, while this one quietly builds a parallel system next to it, and lets the old broken wiring stay switched off entirely. Now, here is the part that separates this from marketing copy, and it is worth sitting with, because the headline on this video could easily oversell what's actually been proven so far. Everything described so far happened in rabbits, not humans. The animals that had lost their auditory nerve regained the ability to respond correctly to spoken commands, and researchers confirmed the closed signal loop behaved the way a real auditory pathway does. But a successful animal trial is a proof of concept, not a finished treatment, and the two are very different things. Human clinical trials have not started yet, and Xu's team has been explicit that the next step is exactly that: moving this out of the lab and into something a hospital can actually implant in a person, a process that historically takes years, sometimes the better part of a decade, even once a device works flawlessly in animals like these rabbits did. There is also a myth worth correcting here, because a title like the one on this video practically invites it. This device is not a replacement for the cochlear implants that tens of millions of people already rely on and depend on every single day. If your auditory nerve is intact, a conventional implant still does its job well, and nothing about this changes that. What this technology targets is the specific, currently unsolvable case: patients whose nerve is too damaged or entirely missing for any existing device, cochlear implants included, to ever reach. That is a real and meaningful gap, but it is a slice of the hearing loss population, not all of it. And it's worth being precise about that distinction rather than letting a punchy headline blur the two together. And there is the obvious unanswered question sitting underneath all of it: cost. A single cochlear implant, surgery included, already runs into the tens of thousands of dollars in most Western healthcare systems. Nobody outside the lab yet knows what a device layering 4 separate custom components together, a self-powered microphone, a star-shaped neural chip, nanowire memory, and a 64-point sensor array, will actually cost to manufacture at scale, let alone to implant surgically, once it does eventually reach a hospital near you. Zoom out, and the timing here matters. The global market for cochlear implants alone is worth somewhere around $3 to $4 billion a year right now, and industry analysts expect it to grow by more than half again within just 5 or 6 years, driven largely by aging populations, wider insurance coverage in wealthier countries, and earlier diagnosis through newborn screening programs that catch hearing loss within days of birth. 3 companies control the overwhelming majority of that market: Cochlear, based in Australia, Mehmed EL, based in Austria, and Sonova, the Swiss company behind Advanced Bionics. Together, they account for something close to 85% of every implant sold on Earth, a level of concentration you rarely see outside markets like commercial aircraft engines. Even China's own domestic implant maker, a smaller company called Neurotron, competes within that same 50-year-old framework of electrodes and an intact nerve, the exact framework this new research just stepped outside of. None of those companies, despite decades of engineering and billions of dollars in combined research spending, has published anything that solves the specific wall Xu's team just cracked open in a rabbit, which says something about how hard this problem has been. That does not mean China has automatically won some race to a finished marketable product, because right now, nobody anywhere has a finished product, and turning any lab result into an approved medical device is its own multi-year race in itself. What it does mean is that the first published peer-reviewed proof that this particular wall is breakable, appearing in one of the most selective materials science journals in the world, came out of a university lab in Tianjin, not out of the established, far better funded companies that have dominated this field for half a century, and that alone is worth paying attention to, regardless of the geopolitics around it. The World Health Organization estimates that more than 430 million people worldwide currently need some form of hearing rehabilitation, and that number is expected to climb towards 700 million by 2050 as populations age globally and noise exposure keeps rising. China alone already counts more than 20 million people with a hearing disability, one of the largest such populations of any country on Earth, which helps explain why a lab there, rather than somewhere else, had every incentive to chase this specific stubborn problem. Even if only a fraction of that wider group has the kind of severe nerve damage this technology targets, that fraction still represents millions of people worldwide for whom, right now in 2026, No commercial product on the planet can help at all, regardless of how much money they have to spend or which country's hospital they walk into. There is a bigger story hiding underneath the hearing angle too. This device is not a one-off project for Xu's lab. It is the latest piece of something much larger, an 8-year effort to build artificial versions of touch, sight, smell, taste, and now hearing, all using the same underlying neuromorphic approach and all sitting under patents his own team controls outright, start to finish. Stack those 5 senses side by side, and you are no longer just looking at a single medical device solving a single problem. You are looking at early groundwork for machines, and eventually people, that sense the world through electronics behaving like biological tissue, adapting and fading the way real neurons do, instead of rigid sensors bolted onto rigid processors that only ever switch cleanly between on and off. That is exactly the kind of foundation brain-computer interfaces and next-generation robotics are going to need as those fields mature over the next decade. And it is why labs well outside the hearing world are already watching what Xu's team publishes next. So the open question sitting at the end of all this isn't really whether this rabbit study is impressive on its own. It clearly is. The open question is whether the country that just published the first working blueprint for an artificial auditory nerve also ends up being the one that turns it into something a surgeon in Boston, or Berlin, or Beijing can actually put inside a patient, or whether the next 50 years of hearing restoration get built, once again, somewhere else entirely, by companies that spent decades perfecting the very technology this research just went around. So here is where that leaves things. For 50 years, if your auditory nerve was gone, there was genuinely nothing modern medicine could offer beyond learning to live without sound entirely. And a lab in China just demonstrated inside a living animal that this might not have to stay permanent for much longer. If you want to catch the next deep dive into a story like this one, before it shows up anywhere else, subscribing and turning on notifications is the easiest way to make sure it actually reaches you the moment it's ready, instead of buried somewhere in your feed weeks later. So here is the question I will leave you with, and there's no clean answer to it yet. Once human trials eventually begin, do you think a breakthrough like this gets adopted fastest in the country that discovered it and holds the patents, or in whichever country's healthcare system and regulators move quickest to actually approve it, pay for it, and get it into hospitals at scale? And if you want to see what happens when a country builds an entire manufacturing base around chips the rest of the world thought it could never produce, the video on China's memory chip breakthrough covers exactly that story in full, start to finish, and it's linked right here for you to watch next.